Okay, we are going to continue with chapter 5, problems and examples. So right here the question is, how do we connect these 4 resistors in parallel? Remember that in order for 2 resistors or 3 resistors, in this case 4 resistors, to be connected in parallel, we can only have 2 nodes. A parallel circuit has only 2 nodes, node A and node B. So that means that all these resistors have been connected to node A, and the other side of the resistors have to be connected to node B. In more general format, we say that the resistors have to share the 2 common terminals. So let's see. The solution would take, I start with this value, connects to this resistor, 1. Then I take the other terminal, connect to that resistor. Now they are in parallel because they share both terminals. I move on. Now I need to make this resistor in parallel with this resistor. So this connects to that in one end. The other end has to connect to the other side of the resistor. Now I have to connect this resistor in parallel with that resistor. So I take the one end, I go across, I connect it here, and then I go the other side and I connect it here. So now these 4 resistors are connected in parallel. So if I redraw it, I can identify my node A and my node B. Again, for a circuit to be parallel, full parallel can only have 2 nodes, A and B, and all resistors have to be connected across those 2. So how do we find total resistance? We have a resistor, 3 different resistors connected. Let's check, they are connected in parallel. So the formula that we learned was 1 over the sum of the resistors. So the sum of the reciprocals of the resistors, the reciprocal of the sum of the reciprocals will give us the total resistance. So I just substitute the values, 1 over 100, 1 over 47, 1 over 22. I find the reciprocals and then I divide 1 by that and it gives me 1303 ohms. It's important to remember that the rule, if it is a parallel circuit, we have to have the total resistance be smaller than the smallest value of the parallel resistors. In this case, 22. We get 13, so we satisfy that. Now we are going to add another resistor to the previous circuit and see how it affects. So the new resistor that we are adding is a 33 ohm. Again, we are going to add the reciprocals of the resistors and find the reciprocal of the sum, and that's going to give us 9.34 ohms. In this case, the resistor decreased, and in observation here, if we would have added a huge value of a resistor here, the value of the resistor would maybe not have decreased as much. It went from 9/13 to 9, but what would have happened is that we would have never gone above 22. Okay, so we're always going to follow that threshold that it has to be less than 22. In this case, the value of the resistor added was small, so the overall resistance came down. Right here, they're asking us to find the total resistance. In this case, we have 2 resistors connected in parallel, so we could use the special formula for 2 resistors, which is the multiplication of the 2 resistors divided by the sum of them, and we get 222 ohms. We can use the regular formula, which always works for any type of n number of parallel resistance. 1 over R1 plus 1 over R2, and we get 222.18 ohms, which is the same as using the special case for 2 resistors. Notation for parallel resistors: R1, then we have a double bar, R2. That means that R1 is in parallel to R2. Okay, sometimes this is a nice notation to indicate once we are solving. This is going to become useful in chapter 6. One of the applications of parallel circuits is that if one branch opens, the other branches are not affected. So this is a nice way because the current has different paths that it can go through. A voltage in parallel circuits. So right here we have two parallel circuits. We have our voltage source, and then we are going to find the R total. We can use the formula because we only have two resistors, so we get that it's 3590. We can find our I source using Ohm's law, which is voltage source divided by R total. We get a 278.57 milliamps. Now using Ohm's law, I'm going to find V1 is equals to I1 R1, but in this case I1 is not the same as I total, and I2 is not the same as I total. That was the case for a series circuit. In a parallel circuit, if we analyze this circuit right here, we see that this node or this connection right here is the same as this point right here. This point right here is the same as that point right here. So this resistor is connected right across this voltage. Therefore, the voltage across this resistor, it is the same as the voltage source. So that is one characteristic that parallel circuits have. If they are connected directly to the source, they have the voltage of the source across them. So if it's a full parallel circuit, we assume that the voltage across the resistor, it is equal to the voltage across the source. So now what changes is the current. So I'm going to find I1 to be at voltage 1 divided by R1, which is 100 milliamps, and then I2 is V2, which is also the source, divided by the current, by the resistance. So I get 178.57 milliamps, which is important to notice here that this one is almost half the value of this other resistor, and we almost got double the value of the current. So the current is totally dependable on the volt of the current value. So if the resistor is small, the current is going to be large. Why? Because current always tries to find the easier way to travel. And then we're going to do KCL at node 1. So let's identify node 1 here. This is a node because we have several components connected to it. We have the source connected to it, we have R1 connected to it, and we have R2. So a node is something that has two or more components connected from, or two. So let's do KCL, which is Kirchhoff's current law at node 1. So let's draw the currents. We have I source coming from the voltage source. Then we have I1 going across R1. Then we have I2 going across R2. What is KCL? It says that all current entering the node are equal to all currents leaving the node. So the first thing we have to do is assign a polarity, meaning that I can say positive are all the currents entering the node, negative are all the currents leaving the node. This is just conventional. You can choose whatever you want, but keep track of the sign and be consistent. So if for this node, in this case we only have two nodes, but in chapter 6 we're going to have several nodes. So right here it's important that you keep consistency between positive and negative. So another way of writing KCL is that the summation of the currents is equals to 0. So let me redraw here. I have my I source going into the node, so that will be positive, and then I have 1 leaving the node. I have I2 leaving the node. So if I use this formula, I'm going to say I source is positive minus I1 because it's leaving minus I2 because it's leaving is equals to 0. Then I solve for I source and I say that I1 is plus I2 should give me I source to be 278.57 milliamps. If I use Ohm's law, I can say that V source is divided by R total, which is 278.57. So this is proof right here. We said before we described parallel circuits as being current divider. So this is one of the major applications of parallel circuits, being current divider. So we are going to do this example in the next video.